And hello, welcome to this video. So in the last video I briefly talked not quite briefly, talked quite extensively about how the information from the entity collection flows all the way down into the create behaviors virtual void function within the simulation class. Now if you've been following the series so far, you can see that the thing gets gets kind of complicated. Okay, you know, somewhere in here is where the behaviors from the entities, okay, entities are the components essentially, okay, and behaviors are the way, let's just get this out of the way. Behavior in circuit, behavior biasing or biasing. Okay, so what's biasing? Biasing in circuits is actually setting the initial operating conditions. So these are actually, whenever you see the word biasing, is actually it just means you're setting the initial conditions, current and voltage. Okay, so that's why the terminology kind of flows over. Whenever you set in initial conditions, you use the word biasing, and behaviors are essentially how you sort of set up your ODEs and matrices, just based on the components that are there. Okay, so somewhere in here is our answer to you know, where are the matrices going, how do you collect the behaviors, and how do you put them into the matrices. Okay, unfortunately it's as I kept looking and looking around the source code, I just kept going around in circles because I could not find exactly how this thing worked. I just kept going around in circles. Okay, so I don't want to bring you through that. Then the other idea I toyed with was, okay, maybe I will just make my own version of the simulation class. Okay, I will make my own version of the simulation class, and what happens after that is that I will just start introducing all sorts of print statements. Okay, all sorts of print statements within the code here. Okay, so right, I can actually introduce a console write line within here, and then see at each point what exactly are these entities that we are talking about, what are these arguments. You know, all of these don't really have any idea what these are. Alright, and then you have these entity behaviors. You're actually building these entity behaviors. Okay, so what exactly are these behaviors? How are they going to pan out in real life? Okay, turns out and I tried that. Okay, I tried that and it is a lot more difficult than I thought. Okay, so basically it's this. Okay, I copied over the simulation class, the biasing simulation class, and along with all its partial classes, and of course DC circuits. Okay, DC simulations actually inherit from the biasing simulation class. Biasing simulation in turn inherits from simulation class. So DC actually allows you to do that. Okay, it inherits from biasing simulation class, and yeah, essentially if you make your own if I make my own version of a DC circuit, and this is essentially over here the tutorial, right? You have a DC circuitry, and then we have the run code here. The run code actually does all the setup and creates all the behaviors, and then starts executing the simulation. Now if I make my own DC class and I tried to, you know, set that up. Now in theory I could start printing statements all over, and I can sort of learn the inner clockwork of this simulation class, right? So I made something called a diagnostic simulation, which is an exact copy. Let's take a look at diagnostic simulations. This is an exact copy, almost an exact copy of the SpiceSharp simulation class. Okay, I just added the word diagnostic in front, and then of course I had to change the constructor. Okay, diag diagnostic. Okay, I changed the constructor here. So I changed the constructor here. Everything else is pretty much the same. Okay, and then I had to put the namespace in SpiceSharp Simulations. Now, problem is this, right? As I actually tried to, I wanted to so-called segregate this class into a different namespace, and I don't want to clutter the SpiceSharp Simulation namespace, and eventually I was hoping to even make my own fluid simulation namespace, right? Moment I do this happens, right? Okay, so I have my .NET watch over here. I will have an exit code 1, and it will complain of a lot of things. Okay, so I tried fixing the bugs using putting these in using SpiceSharp Simulations, SpiceSharp and SpiceSharp General. Why is that the case? Because one of the things that was missing is the throw now. Okay, why don't I show you the error? Okay, I'll go to the top. I will comment this out, and then I will show you the error which I got. Okay, and I'll show you the error which I got. Okay, it says what? iSimulation state cannot be found. Why? Because we are not using the SpiceSharp Simulation namespace. Okay, fine. We will use the SpiceSharp Simulation namespace, which contains all the other classes that this diagnostic simulation or the simulation will eventually be dependent upon. Okay, now I do this, you see what happens. Okay, it says what? TypeNotFoundException is missing. Where is this TypeNotFoundException source code actually? Okay, so the type I tried to look for the TypeNotFoundException. So well, let's go to simulation.cs. Okay. Oh yeah. In case you were wondering, I was actually running VS Code within the browser. That will come in handy later when we want to search for code. So what was I looking for? Okay, I was actually looking for this thing called TypeNotFoundException. So let's look for TypeNotFoundException. TypeNotFoundException. Okay, and then we'll see SpiceSharp Diagnostics TypeNotFoundException.cs. Okay, that's fine, and you see it's found in the namespace SpiceSharp. Okay, great. So let's use the SpiceSharp namespace. That's quite simple. That will get rid of the TypeNotFoundException. Okay, and I'll save it. You can see it will start building the project again, and I'll have an error code. This time is because of a compile error. Now the next error that I find is that the name properties doesn't exist in the current context. Okay, what properties are we talking about? Okay, it says that this properties thing right here, this under this SpiceSharp warning, okay, properties, resource simulation, node entities, all of these things are missing. Okay, all of these things are missing. So there are two times where this thing properties is being used, but I don't see anywhere in this whole code that this specific properties object is being used. So my conjecture was that this properties object must be somewhere hidden inside the SpiceSharp simulation namespace. Hey, but wait a minute, I was using the SpiceSharp simulation namespace. Why is it doing this kind of thing? Okay, so my guess is that all these properties, this property object is possibly something else in there. Somehow the class is declared such that when we put this SpiceSharp simulation or this simulation class within the SpiceSharp simulation namespace, you're able to access this properties object somehow. I do not know how, but it is there. So that's when I say yes, let's try looking for this properties object. Okay, let's look for properties, and if you try to look for properties in here, you'll see there are at least 50 pages of results, and these properties things we only see it mostly in the SpiceSharp component semiconductor MOSFETs level 3 model temperature, something like that. you'll see this properties thing being so-called defined here, right, as one of the properties. Yeah, these properties are a class property, all right, which is, I mean, it sounds confusing, but that is what it is. That's how the code is being done, right? And the namespace is under SpiceSharp components, MOSFETs level 1. Okay, great. Or MOSFET level 1. So these things are under the semiconductors things, which in a normal simulation we don't even bother using. Why is this properties object being found here? All right, so most of the properties things that we find are inside the semiconductors thing, which we know has absolutely nothing to do with a simulation without semiconductors. I mean, in a generic simulation, you cannot expect it to have semiconductors. So where does this properties object actually come from? So that's where I start using, okay, VS Code within the web. Okay, how do you do it? Okay, just press the full stop button with it. When in your GitHub page, you will be able to access VS Code. Okay, you will be able to access VS Code. So use VS Code GitHub. Okay, you are actually able to use VS Code in GitHub, which is pretty convenient because now I can use Vim bindings. As you can see, right here, my extensions, I have Vim over here, VS Code Vim enabled, so I'm able to use that. Not only that, I also can use the search thing within VS Code, which is much more powerful, I think, than much more powerful and faster than the GitHub one. So let me close this thing. Let's look for properties, and maybe we'll look for maybe some class properties or some properties object. Okay, and then I'm only going to search within the CS files because it says here files to include star.cs, and okay, we will see this properties object being thrown all around here. Okay, see properties. Okay, properties again, properties here. All of these are inside our sparse vectors. Okay, under SpiceSharp algebra. Okay, for some reason using a SpiceSharp algebra, that is able to help us get our properties. So, right, let's check out whether we have SpiceSharp algebra. Okay, we don't really have SpiceSharp algebra here. Okay, but we can of course include it just to see what happens. SpiceSharp.algebra. I can guarantee you it still has the same error. Okay, we still have this properties is missing. Okay, SpiceSharp algebra doesn't really help there. Okay, even though the properties are the properties are being used here. Okay, see, properties are being used here. So okay, somehow it is being defined here. Where is it defined? I do not know. Okay, see, even in the biasing simulation, biasing.cs, you will find the properties thing here. Okay, so I look, and what do I know when I look at the tree again? I find that okay, there is some properties folder over here under resource designer. Okay, this is a SpiceSharp properties. Okay, SpiceSharp properties, and it has one class called resource, and this is auto-generated code. Okay, so there is some kind of property here. Okay, fine. Let's try using SpiceSharp properties and see what happens. Using SpiceSharp properties. Okay, still the same problem. So this one doesn't help. This one doesn't help. This one doesn't help. Oh wait, this helps with some with the earlier errors. Okay, so again, I don't know. Yeah, this already gives us a clue though as to what's going on, because as you can see, the code is generated by a tool. Yeah, the code is generated by a tool. So that means that, hey, wait a minute, not all the code that we use here is being generated, or rather being you don't see all the code, you will not see all the code that is being used being explicitly written. Some of it is auto-generated, unfortunately. Fortunately or unfortunately. Okay, so alright, the other place I found properties is under SpiceSharp General. You see? Oh, under General. Under General, we have reflection, type dictionary, array constant utility.cs. Okay, I kind of got a little bit frantic, and I started looking. Okay, in fact, the SpiceSharp General namespace, I was looking at it here because all of this has some sort of a type dictionary, because it was looking for TypeNotFoundException. Okay, throw new argument exception, and okay, let me look at it. Okay, TypeNotFoundException. Yeah, TypeNotFoundException. Somewhere it was being thrown over here. Okay, but okay, I don't know. I can't remember what I was doing. But anyway, I found this other namespace called SpiceSharp General, and even then I tried to use it. Okay, hopefully, you know, it's a hit or miss thing. I might find it, I might not. Okay, all of this was not able to solve the problem, as you can see. The only way to solve the problem was to revert this namespace, change the namespace back to SpiceSharp Simulations, and all of a sudden the code will work for some reason. Okay, I don't know why. Okay, so yes, we can make our own diagnostic files, but it has to be within the SpiceSharp simulations. And even then, if it's there, there's so much going on under the hood that it's very hard to find out what's going on. Yeah, and it's not being done in explicit classes, because what the thing is that this properties okay, where is it? Yeah, this properties object here. In this properties object here, we don't even see it declared explicitly, and you will not see it even declared. You will not see it declared in parameter set collection or anything preceding over there as well. So, and not only that, we also have auto-generated code. Okay, the properties class, the property classes itself, this resource designer thing here, well, at least, yeah, SpiceSharp properties, this is auto-generated code. So what all this goes to show, yeah, of course I did take a dive into the SpiceSharp generator just to see what kind of auto-generated code there is, because this SpiceSharp generator is where SpiceSharp the SpiceSharp code for generating behaviors, as you can see, the behaviors generate the code that generates the behavior generators, the source generator code here, all of this is being done using auto-generated code. Okay, the constants as well, and even properties. You see, generated properties is it says what it describes an auto-generated property. So somehow this SpiceSharp, in a sense, this generator code helps us be very flexible with properties and everything. You can see the property thing is here, but you see, the thing is that wow, there's so much things going on under the hood, so many things going on under the hood, and they're all very tightly coupled, which kind of defeats the purpose of, you know, solid principles, where you try to have things really modular, you try to have things extensible, but now we have dependencies that are kind of going everywhere, you don't have one object neatly called by another object. Now you have auto-generated code as well. You have events that codes, different objects are communicating with each other. Yeah, it's very hard to see what's actually going on if I didn't write this all from scratch. But of course, each class is like not thousands of lines long. You can see all of these lines of code are pretty short, but you kind of keep having to hop here and there. It's really difficult to still to see what's going on, unfortunately. But you know, that's where we are right now. Okay, so the thing is this, it's kind of difficult to find out what's going on under the hood, because not only do we have this funny properties object which we don't know where it's coming from, and also how do we even know where this properties object, where is it coming from? Okay, so long story short, I just decided that hey, this thing is way too complicated to be worth the effort to try and build a simulator class from scratch. Okay, if I want to build a flow simulation class, I do not build it from the simulation abstract class. I mean, I do not try to build it from this simulation.cs class, and I try to import all these methods into some other thing. Okay, I'm just going to go a lot higher in level. Alright, and I use SpiceSharp the way it's meant to be used. Okay, it seems that probably you do not want to touch anything under SpiceSharp simulations. Okay, you probably want to inherit these classes as is, not do anything else to it. Just treat it as a black box. Everything is working under the hood, and then we'll just go on to our next thing. Okay, so the closest thing we can actually look at is, you know, this modified nodal analysis, or rather, we'll try to look at where is it? Yes, we'll try to look at how SpiceSharp actually does custom resistors. Okay, because custom resistors are, they actually kind of provide a template class for us to check out, you know, what's how do you design custom components, right? And well, for fluid flow, we have a very non-linearly behaving flow resistance, right? The friction factor behaves pretty non-linearly with, or the pressure drop kind of behaves non-linearly with flow. We have a sort of 1:1 correlation where voltage can represent, 1 volt can represent like 1 Pascal, so to speak. I mean, we can do that sort of hand wavy conversion thing, and 1 ampere can represent 1 meter cube per second, kind of kind of a volumetric flow rate. So PV, the pressure times volume will equal to power, and then will equal a power unit, and also the current times voltage also equals a power unit eventually. So eventually, yeah, that can actually work. Okay, that can actually work because the units kind of work out pretty nicely. Of course, you can use a mass flow rate basis as well, but yeah, nothing really works as well as this volumetric flow rate, because if I use mass flow rate, then the pressure units will be P over rho rather than P. But anyway, so yeah, so the thing is to sort of use SpiceSharp as is. Don't try to make a new simulation class for flow simulation. If I'm doing it, I'll have to make a new SpiceSharp simulations kind of a thing. I have to make a new SpiceSharp implementation. As you can see, I have implementations like DC, which does this parameter sweep thingy, but I'm not that interested in that. The thing I'm more interested in probably is this OP. OP is called operating point. What's operating point? Operating point is operating point analysis. Okay, operating point analysis is this, right? Operating point of a circuit is the static solution to a circuit. All voltages and currents are assumed to be constant over time. So operating point in chemical engineering speak is called steady state. Okay, steady state calculation is pretty much what we want to have in a flow simulation. Okay, because pretty much when we have a certain volumetric flow rate, or we have a certain pressure input to the pump, the flow will kind of equilibrate almost instantly. Okay, so this, at the very least, we want a operating point calculation, which is pretty much steady state. And yeah, we can actually just use this kind of we can actually just use this kind of what do you call that? Yeah, we can use this thing here, this class here as a template. Okay, we can use this class here as a template. All right. Everything under the hood, unfortunately, we cannot pry apart that easily, because everything is so tightly coupled and optimized to run within itself. If I change something, it will kind of break the whole thing. Okay. Of course, I can make a new simulation class. Yeah, I'll probably take too much more effort than that is really worth it. Okay, so rather just use SpiceSharp as it is and just design a new component. Okay, so the nonlinear resistor is here as such. Okay, nonlinear resistor inherits from component. So if I were to make a pipe class, I can also make it inherit from component. I copy and paste everything here. I do not change anything. Okay, so the node A is well, I can change node A to something like an inlet, node B to something like an outlet. And if we take a look here in the custom components, okay, node A is the inlet, node B is the outlet. Okay, again, A is the inlet, B is the outlet, right? And then we use the connect function here. So yeah, I think I'll change it to inlet and outlet. Okay, I'll try to call it inlet and outlet so that because we'll just call it inlet and outlet. You shouldn't call it node A and node B, because unlike in current simulations, or rather electrical current circuit simulations, you don't have AC things where your current keeps flowing back and forth in a sinusoidal wave kind of a thing. For most flow setups, it behaves a bit more like a DC direct current kind of thing, where flow only goes one way. You hardly ever have reverse flow, unless it's unless it's a thing. Okay, but by and large, you can just copy and paste the code like that. Okay, and you can see nonlinear resistor. You don't really see you don't really see very much what do you call that? You don't really see much code here, except we have a new base parameters thing here. Yeah, we have a new base parameters thingy here. Okay, and this base parameter thingy actually falls under the SpiceSharp components nonlinear resistor kind of class. Let me use a VS Code here so I can switch between the things a little better. So I'll set up the web editor. Okay, we'll go to SpiceSharp test, examples, custom resistor, and there you go. See, so you see this close the readme.md. So this nonlinear resistor is being used here in this nonlinear resistor test. So that's a test thing where you actually execute the code. But here's the thing. here's where the nonlinear resistor class and constructor is being defined, right here. Okay, so you see here we use SpiceSharp behaviors, SpiceSharp parameter sets, and SpiceSharp simulations. Okay, maybe I can try using the SpiceSharp. Forget it, never mind. I will not try debugging that simulation. I'll just stick to this. Yeah, so here's pretty much the thing we use for SpiceSharp simulations. Yeah, nonlinear resistor is the name of the component. Okay, and we are using the namespace SpiceSharp components nonlinear resistor behaviors. Why is that so? Because it will all the equations that you want to have found within here. Okay, nonlinear resistor behaviors. Okay, this is the namespace nonlinear resistor behaviors. So all of these things we discussed before about matrix location, element sets, all of this will be sort of over here. Okay, so you just copy and paste them over. If you have one inlet, one outlet, do not touch anything else. Right, so the next thing here is to so-called load the Y matrix and right hand side vector. Okay, so this is where the so-called biasing behavior starts. Okay, but the biasing behavior thingy starts. Alright, so all of this here is where we have our Jacobians being defined. Okay, you can see here this is where we have the Y matrix. So we have this elements dot add method. The Y matrix is right over here. Okay, so it will be added in this order: YAA, YAB, YBA, YBB. Okay, and yeah, you should add it in this order, right? So yeah, the partial derivatives will be kind of different. Yeah, it'll be kind of different, but just to make sure it's correct, we can actually yeah. My goodness. Yeah, the things here we have we have 4 partial derivatives here, and we are supposed to put these partial derivatives inside this Y matrix right here. Okay, so I'm assuming that this is actually the first partial derivative that you see here, YAA. So it's the equation over the contribution to the equation over A differentiated with respect to the voltage at A. We can just assume that this voltage at A can be so-called taken as the pressure at A, which is the pressure at the inlet, right? So this second element here will be this YAB, which for linear resistor is -1/R. YBA is the third element, YBB is the fourth element. So that's partial FB, partial VB. Alright, so that's how we do it. And then we load the right hand side vector as well. So we'll actually need to take a look at the right hand side vector, which is the Jacobian of A at x over k minus the contribution due to this what do you call that? Yeah, contribution of the current, okay, which is f of A. Yeah, the contribution of the current due to this resistor here. Okay. So these are the two right hand side vectors. Okay, so you yeah, say all other Y matrix contributions are 0. That's for the resistor. Okay, similarly we calculate contributions from right hand side vector. So this is the setup. Right hand side vector. Yeah, so well, we have these two right hand side vectors being calculated, and these two right hand side vectors are essentially, I think, if I'm not wrong, these are current units, V over R. These are current units which are being placed in the right hand side vector based on classic nodal analysis, because on the right hand side all of these are actually current units. Okay, if you have a modified nodal analysis as you do here, we will just have let me see, this one times this, that will give you the fourth. Yeah, this current source here, this current source here will instead be sort of a voltage thing rather than a current thing. Yeah, let's see. I mean, yeah, so by default for all resistors, we will have current on the right hand side. Okay, this all the currents will be on the right hand side. So you see, C is for current here. So right hand side vector all will by default for resistors will always be loaded with currents, except when we talk about the right hand side vector for current source. Then the right hand side vector, right hand side will always be this voltage thing. Of course, under the hood, all the indexing will be taken care of by all the things, all the underlying classes as we discussed before. So maybe it's not all that a waste to actually go and look under the hood as to what's going on. Then pretty much you're done already. Okay, if we have we also have this thing called base parameters. Okay, base parameters will be under context. Get parameter set, get parameter set base parameters. Okay, so this will get our resistor parameters. We want our A and B resistor parameter values. Where is this base parameters being set up? It's over here. Okay, so you need to have all these special keywords like generated parameters. It must be a partial class base parameters, which will inherit from parameter set base parameters. Okay, so we make a public double A, public double B, all that kind of thing. Okay, and you see that over here, we actually make these base parameters. We instantiate it, and then what happens to it? Okay, where is this? Yeah, somewhere under the hood is all being taken care of. I'm not going to bother looking anymore. It's a very time consuming. Okay, more or less, but suffice to say, all the parameters you could ever use inside here, you could ever use inside inside our parameter set will be placed over here. Okay, and all of these of course are doubles and all that. We can actually use units, okay, base units and all that over here, but yeah, I will not go too much into that. All to say that, okay, how you actually calculate the partial derivatives. Okay, you actually calculate them sort of in a manual manner right here, where you actually do literal derivations. Okay, for example, FA, which is over here, is 1 over VA over R minus VB over R. Okay, and then we do a partial derivative with respect to VA. We'll just get 1 over R on the right hand side. That's for linear case, but for non-linear case, then you have to do a lot more work. Okay, we have to do a lot more work, especially potentially for a Reynolds number kind of a thing. So let me scroll up until we find Reynolds number. Okay, Reynolds number is here. You can see it's a very non-linear profile, and it's dependent. I mean, yeah, we look at the friction factor and the pressure drop. All of these are pretty non-linear indeed. Okay, very non-linear. So somehow we'll need to do partial derivatives on this. Okay, which I can just take for resistance, I can just take this okay, never mind. Yeah, so yeah, somehow I'll need to include these equations into my pipe class. Of course, I can consider entrance effects and everything as well, but let's just keep things simple first. Yeah, maybe like elevation and stuff we'll do it a bit later on. Okay, I'll stop for now, but that is the plan going ahead. We'll just modify this nonlinear resistor. We'll start calculating the how we can actually deal with this very complicated correlation. The A and B all somewhat dependent on Reynolds number, power 16. I do not want to do this by hand, honestly speaking. Yeah, being very honest here, I do not want to do this derivation by hand. I might even use a central difference approximation, and I will differentiate it with respect to some Reynolds numbers. Okay. Yeah. In fact, if we are actually what do you call that? Anyway, so I think next time we'll just figure out. Yeah, we'll make a non-linear pipe or something like that. We'll pretend we'll convert it into some sort of electrical component. We'll stuff it into a circuit and we'll see, hey, does the flow correlation actually work? Okay, so we'll maybe connect it to some fixed voltage source, and maybe I will change that voltage source into a pump. Okay, with a corresponding pump curve. Okay, but I think that's all for now. I don't know. This thing is driving me, it's confusing me a little bit. So yeah, I'll stop the video for now. But this is the plan moving forward. Okay. See you next time. Okay, make Control Alternate J. I'll bring it. Yeah. So I think next time I'll try to make a new nonlinear component, which is the pipe. And we'll try to derive all the necessary properties from there, what I should be adding to each of the matrices, and I'll see you next time. Bye bye.